Hello, Rakesh, I am audible. Please just confirm.
Yes, you are.
Okay, fine. So we'll start within 5 minutes. Let us wait. Maybe a few students will join. Then we'll start. Okay, so let us start. So today actually we are going to solve some questions regarding your week 10. So the week 10 is about the differential analysis of the fluid flow. This is the second lecture. And I think the first lecture of week 9 we have covered already the differential analysis. So here we'll discuss about the Navier-Stokes equation and part 2 and part 3 of the Navier-Stokes equation. As Navier-Stokes equation is very important in case of your fluid mechanics or fluid flow you can say. So that's why we will more focus on the Navier-Stokes equation concept in week 10. So before moving ahead a little bit, I have some concept regarding your equidistance streamline and other things. So just I want to discuss because this is very important, this concept, the equidistance streamline. As we have discussed earlier, I think 2 or 3 questions already we have discussed about the equidistance streamline, whether the normal acceleration exists, whether tangential acceleration exists, if the streamline is equidistant or equispaced. So here I have some little bit concepts regarding that, then we'll move on the today's topic. So as we know, If you have the curve streamline like that, I want to draw here. If you have the curve stream like that, then the centrifugal concept will come. The centrifugal force concept will come. So as you know, the velocity is in the centrifugal force is omega r, or you can say 2 pi r by t, because omega is 2 pi by t. So acceleration is here v square by r. In case of curved path of flow, you have acceleration, that is normal acceleration, v square by r. If the flow path is curved, the normal acceleration will exist always. If the flow path is curved, if it is your streamline is straight, there is no normal acceleration because of no curvature in the flow. But if you have curvature in the flow, then it means the normal acceleration will exist. But what about the tangential acceleration? The tangential acceleration is nothing but the acceleration along the streamline. Remember please, the acceleration along the streamline. Let us suppose here the acceleration is something. Let us suppose here is 10 unit, and here is the 11 unit. Then you have the some acceleration. The along the streamline I am talking about, the tangential acceleration. So the case is here, the first case, you have the equidistance, that is the between the two streamline space is same. Yes, here is also S, here is also S. So this is the case. So here normal acceleration will exist because of your equidistance. Now about the tangential acceleration. So why tangential acceleration not exist here? Because of, as you know, the mass flow rate is nothing but rho, that is density of water, and the area between the whatever the here area we have, this area between the streamline and the velocity. So if the streamline is equidistance, it means what? And flow is incompressible. The here in this question we have assumption the flow is incompressible, right? So if the flow is incompressible, rho will be the constant, and area also will be the constant because of the S is your, because S, the between the distance between two streamline is constant. Now the only things is remaining velocity. So what about if, as per the mass flow rate, so conservation of mass, so velocity, if you want to check the mass flow rate at point A and at point B, so the velocity, if the velocity will be equal at both places, then you can say the mass flow rate is constant at point A and at point B, because of two things you have already constant, only one variable. So if you want to make the constant things constant mass flow rate, so you have to change v. But whether we will change or not, so here we will not change because of area is constant. If area will somehow decrease or increase, here we have some increasing or decreasing area. So here we'll discuss about area between the streamline, remember please. So in that case, as we have seen here, the velocity in equidistance case, the velocity will be constant at two places. It means there is no acceleration along the streamline. So that's why the tangential acceleration will be zero in case of such type of case of a streamline. But here, as we can see here, uh, the next case. In next case here, we can see this is the main thing. Here the distance between streamline is S1, here is S2. Similarly, the S3, S4. So if the distance is decreasing, means what? Area is decreasing between the streamline. So for maintaining the conservation of mass, you have to change velocity. So definitely at point 1 and at point 2, velocity will be the different v1 and v2. So it means if the your flow curvature, if the flow path have the curve, then the normal acceleration will exist, and tangential also exist here because of the here streamline is not equidistance. So this is the concept behind your equidistance streamline regarding the tangential acceleration and normal acceleration. Hope you all will get, and these are the concept we have discussed earlier, so here is no meaning, but this was the very important. So now let us move with your actual things. So these are the questions. Actually, these are the slide I have prepared some in the previous year when I was discussing. Some student was asking about these type of concepts, so that's why this I have kept it here. Okay, so Navier-Stokes equation, as I have discussed, this is very important equation for the fluid flow. So I'll not go in detail because sir has already discussed. So here we'll see some key concept, and directly I want to show you the equation, the Navier-Stokes equation. Here you can see very clearly in the Cartesian coordinate, the continuity equation and the Navier-Stokes equation. So this is the continuity equation, and these three is the Navier-Stokes equation in three-dimensional. Remember please. So here you can say this is the x component of incompressible Navier-Stokes equation. Remember please, here the assumption is incompressible. Here y component of the incompressible Navier-Stokes equation, and another one z component of incompressible Navier-Stokes equation. The difference here, as you can see, these things is same everywhere. Here also, here also, here also. What is changing here? Here is u, v and w. Again here you can see x, y, z. Only coordinate is changing, and the gravity in x direction, gravity acceleration in y direction, and this is z direction. Now this is your viscous force, which is with respect to u, with respect to x, y, z, u, and similarly here for v, similarly for w. So these are the concepts. When you will write in terms of your when you will compact this, then you will get this equation. Like in the calculus form, if you want to write then you will get, that is the differential form. If you want to write, that is the diver. Here as you know, this is your del operator. So del operator is nothing but d by dx plus d by dy j plus dy dz. Okay. So you can say here in the vector form you can write like that. In the Cartesian, in the vector form you can write like, when you will write this equation have all three components because you are writing with the vector form. So generally you remember please, your continuity equation, remember, for incompressible flow we are talking about incompressible continuity equation, that is your del into v equal to 0. This is vector form, and Navier-Stokes equation is rho sometimes capital D v by dt, known as the material derivative, remember please, equal to minus del p, this is p not rho z plus del square not v square by v vector. So as you know already, so del is this, del is del by del x, del by del y, del by del z, and v is what? Your v is nothing but u in I, v in j, and w in k direction, that is xyz direction. When you will multiply these things, you will get what? You will get nothing but, you will get the multiply with I will be 1, and you will get du by dx. Similarly, when you will multiply this del v by del y you will get, and del w by del z you will get, and finally equal to 0. So you will get the similar thing, but in the vector form is very easy to remember. Only you have to play with the your divergence and all. So this is the concept, remember please. So now we'll move on the direct question. So here I have some example as I will upload this PDF in the Google folder, so you can go through that. One thing also remember please, the complete solution of Navier-Stokes equation is not possible. Means possible, but till now no one solved. For a complex problem, I am talking about the complex problem, it is very difficult to solve. So we'll go with the various models. Turbulence model. Model means here the equation of the set of equations, nothing but. So the first question from today class, the incompressible Navier-Stokes equation for Newtonian fluid in vector form are best written as. So you have the four option A, B, C, D. So please just try to write your answer in the chat box. I am waiting. So please just think on that and try to write your answer in the chat box. You have four options. So as I have discussed about the Navier-Stokes equation, so this is just basic question from here. So please just try to solve. Think on that and try to write your answer. In the chat box you can write very easily. So please within 1 minute just try to write, then I'll discuss about in detail. So let us discuss. So this is your in vector form. So just I have discussed the Navier-Stokes equation. What is Navier-Stokes equation? So this is your incompressible, remember please. Incompressible Navier-Stokes equation. So what will be the correct form, whether A, B, C, D? So as you can compare from here. Just I want to show you first. This is I was discussing. Let me just show you. Yes. Here you can also see. This is yours. So del V by del dt dv by dt you can write del V by del t plus your this is your local acceleration, or here you will get the term of the conventional acceleration, means u du by dt. If you are writing in x direction, here it also will come u plus v du by dt dx dy plus w du by dz. So this is the combination, and rho will be, because this is incompressible, so rho will be the constant. So you can just compare. And another thing also important, let me just, so here you have one pressure term, one the body force, another is viscous force. So you have to remember your acceleration term is equal to, I will write here, wait few minutes. Okay, so here your the Navier-Stokes equation is nothing but the Newton's second law. Force, that is your force is equal to rate of change of momentum. Rate of change of momentum. So based on this concept, we have derived only your this Navier-Stokes equation. So this part is showing your acceleration, that is rho is related with your mass, because as you know the density is nothing but mass by volume. So it is related to mass into acceleration. This is your acceleration is equal to all forces. So all forces included pressure force plus your viscous force plus body force. So these three force equal to acceleration. So this is nothing but force is equal to mass into acceleration. You have to think on that. So once you will check here, so this represent your acceleration, this is pressure force, viscous force and body force. So option A will be correct here, remember please. So always remember your, in Navier-Stokes equation we consider all three forces, pressure, viscous and body force, and acceleration part will be there. Now, so here some comment on that. The incompressible Navier-Stokes, that is constant rho, include material, that is material means convective acceleration. Convective acceleration, pressure gradient and viscous diffusion. Viscous diffusion means nothing but your the viscous part, this part talking about, and the body forces. So remember please. Next question, very easy question. Question number 2, very easy. The no slip boundary condition at a solid wall implies only the normal velocity is 0 at wall. Both the velocity and the tangential shear stress are 0 at the wall. The fluid velocity equal to wall velocity at the wall, that is 0 relative velocity. Option D, only the tangential velocity is 0 while normal can pass through. So you have the 4 option. Just think on that. This is very easy question. I think sir have teach in the first very beginning class. So this concept is very important here. In the week 10, that is your boundary conditions and all. So please just try to write your answer in the chat box. Or you can use mic also if you know the answer. Okay, I will give you 1 minute again for this question. Okay, you are telling option C is correct. The fluid velocity equal the wall velocity at wall, that is 0 relative velocity. Okay, let us see. Yes, you are correct, because as you know we have already, sir have already discussed. So if you have a fixed plate and here you have the movable plate, so I'm going to take two conditions here. One is fixed plate, another is, and the plate is moving with the velocity v. and this is your fixed plate, means the velocity of the plate here is 0 at the bed level. So the fluid velocity here also will be the 0, and here fluid velocity will be the velocity of your plate. So remember please. So this is the concept. So here the fluid velocity equal to the wall velocity. Yes, if wall velocity is 0, then fluid velocity will also 0. If wall velocity is v, then fluid velocity will also v. Okay, now zero relative velocity means there is no difference between these two velocities. Okay, this is a no slip condition, means this is not exactly happened, but we can consider these things. Question number 3. For an incompressible Newtonian fluid, the viscous term mu del square u arises from. So whether it is linear relation between stress and strain rate, that is constant viscosity, nonlinear dependence of stress on velocity, body force acting on fluid, and compressibility effect. So these 4 options you have. So please just try to think and try to write your answer. Within 1 or 2 minutes you can take also for thinking. So please just try to write. Okay, you are telling option A is correct. Okay. So linear relation between stress and strain rate, that is constant viscosity. Yes, you are correct, because we are taking the, as we will see in the previous question, the question number 1, here we have taken only, there is no x, y and z direction your this viscosity term. So we are considering the linear relationship, that is the constant your viscosity. Okay. So now let us move on the next question, this one. The Reynolds number rho, that is, this is your average velocity, remember please. This is average velocity and this is your characteristics length. and this is your dynamic viscosity. Rho is, you know already, the density term. So the Reynolds number represents the ratio of gravitational force to viscous force, ratio of inertial force to viscous force, ratio of pressure to viscous force, and the ratio of convective to body force only. So you have the four options. So please just try to write your answer. Okay, this is very easy question. So I think no one joined. I think student have some network issue. Okay. So anyway, I'll record. So Reynolds number, very easy things. Here is no very hard thing. So Reynolds number is nothing but your the inertia by viscous force. Remember, please. Option B will be correct here. Reynolds number is nothing but your inertia force divided by viscous force. So remember, please. Now let us move on. Next question. So question 5 here is Stokes flow approximation is valid when? The Stokes flow approximation is valid when your Reynolds number is 1 greater than 1. So inertial term dominated. So inertial term dominated. Remember, please, here. Reynolds number is equal to 1. Not exact equal to 1, but most equal to 1. And Reynolds number is less than 1. So inertial term are negligible compared to the viscous term. And the flow is turbulent. Stokes, that is your creeping flow approximation, is valid when your Reynolds number combination is there. So please just think on that. Oh, I think no one joined, so let us move on the direct on answer. So before moving on the answer, I want to discuss a little bit here. So as you know, here in the first question here I'll discuss Reynolds number is nothing but your inertia force by viscous force. So I want to write, okay, VF inertia force IF. So if somehow your Reynolds number is 1, then what will happen? Your IF divided by VF, IF will be equal to your VF. I think someone joined. Okay. So IF is equal to VF means what? Okay. So both forces are equal. If your Reynolds number is greater than 1 means what? IF inertial force divided by viscous force greater than 1 means IF is greater than VF. . That is, inertial force is greater than your viscous force. Similarly, if your Reynolds number is less than 1, so IF divided by VF less than 1, so IF less than VF. So this will be your concept here. Means when your Reynolds number is less than 1, then your viscous force will be dominated. When your Reynolds number is greater than 1, your inertial force will be dominated. So now here you can think on that. Whether this statement is valid. Reynolds number is greater than 1, so inertial term is dominant. Yes, this is statement is correct, but whether it is condition for a Stokes flow approximation is this option A or not. So this is the question here. If less than 1, so inertial term are negligible compared to the viscous term. Yes, here we have seen already. Viscous term will be the high if your Reynolds number is less than 1. So a statement is correct, but whether these statement is your coming under the approximation of a Stokes or creeping flow. So here question is about, okay, let us move on the final answer. So in this Stokes flow, your the approximation is valid when your inertial term are negligible compared to the viscous term. Means your Reynolds number is less than 1. Remember please. So Stokes flow is follow the means it is more valid when your viscous term is that is valid, not more valid. The Stokes approximation is based on your viscous when the viscous term is dominated. Remember. Okay. So if the here you can think on that very important here interpretation is given. Reynolds number is less than 1 means very small. So inertial, that is the convective term. Inertial means nothing but the force due to your velocity, force due to the flow. Whatever the, let us, I want to just give you some pictorial representation. Let us suppose you have some velocity here. So the force due to these velocities of the particle, this is known as the inertial. And with the velocity particle means what? Your acceleration term du by dt, as you know already, du by dx plus dv by dy. So plus v plus w, here is also I am writing in x direction, so dz. So these are the terms, these are the acceleration which is related to inertial force. If the inertial force is less means the your this acceleration will be the very less, meaning these term will be the from the Navier-Stokes equation will be the negligible, means 0 you can write. So only you will remain with these three term, force and your viscous term and your body force. Means when you will add these three force, you will get 0. So here it is written, the term negligible and Navier-Stokes equation reduced to linear Stokes equation. So remember, this is linear Stokes equation with continuity. Option C is correct. Now let us move on the next concept. Next question, question number 6. So taking the curl of the Navier-Stokes equation for constant, you have dynamic viscosity, yields and evolution equation for so pressure, velocity, magnitude, vorticity and density. So you have the four options. So anyone join? Whether okay, still no one join. Okay, we'll move ahead. So just think on that. What is curl, and uh, and if you are taking the curl of the Navier-Stokes equation with constant your dynamic viscosity, so what will happen? So this is a little bit more conceptual question. So if you will think well, definitely you will come up with the correct answer. So let us move. Okay, let us move with the final answer. So here again, your option C will be correct. So you know curl is nothing but, yes, when you will take the curl of Navier-Stokes equation, you will get vorticity here. And what is how we will calculate the vorticity? That is omega is equal to del cross u. This is your rotational. This is showing you the rotationality of the fluid. So what is exact meaning? The exact meaning is I j k del by del x del by del y del by del z u v w. So this is the concept. When you will take this curl, you will get I. How I will just try to, you have to solve with the as like determinant. Del v by del y minus, sorry, del w by del y minus del v by del z, then minus, you are taking j component here, so del w by del x minus del u by del z, now plus k component. So when you will take this, del v by del x minus del u by del y. So you have these three things. So you will solve such type of problem like that. That is the curl problem. But here question is, taking the curl of Navier-Stokes equation, you will come up with the vorticity. So here some concept is given. Curling momentum eliminates the pressure gradient, since curl of the gradient is zero, and produce the vorticity transport equation describing the vorticity creation, stretching and convection and the diffusion. So these are the some concepts you can go through. Okay, so next question is, which term in Navier-Stokes equation is responsible for convective acceleration? Very, very important. So just think on that. Okay. So I'll in the class, because maybe some student will join. So again, I'll take tomorrow class from 7 to 9, same time. And this class is from your the previous, I think on 30th. Let me just see. Yes. Previous month. Yeah. This class was your on 30, but due to some work I'm taking today, but your next class will be on 7 of week 11. Okay, so which term in the Navier-Stokes equation showing the convective acceleration? So what is convective acceleration? You know already. The acceleration term, you have two terms. One is local and convective. So in local acceleration, you have del u by, if I am writing in the x direction, del u by del t plus u del u by del x plus v del u by del y plus w del u by del z. So these three you have three direction, but I'm writing only x direction. So this is your local and this is your convective. So you can write these things very easily. Del dot product u v. So here your del is your del by del x. Here is I, remember, j del by del y plus k del by del z. So these three terms. And what is your v? U I plus vj plus wk. So when you will multiply, I will be the 1 and ij will be the your 0. So when you will multiply, you will remaining, you will come up with only del u by del x plus del v by del y plus del w by del z. But one thing you are missing in the convective acceleration. What? U, V, W. So you have to multiply with again with your V. Once you will multiply with V means you here once you are getting these things, you have to multiply. Once you are getting these things, so you have U, V, W means another you need to one term with U plus V Vj plus Wk. When you will multiply this again, you will get this final answer like that. One thing here is very important, which is we are not having Ijk term. When you will multiply these things, so you have to here Ijk somehow. Then when you will multiply these things, you will get u by del x plus v del v by del y plus w del w by del z. Okay. Okay, finally, let us just discuss the answer here, but think on that, how you will get these things, or you can search on Google whether how you will write from your Cartesian to vector form, how you will write this equation in the vector form. Once you will see, we will get the more clarification on that. Okay, option B is correct here because we are talking about the convective acceleration and local acceleration also you can. This is the local acceleration, but we are not discussing here the local acceleration, only convective acceleration. So option B will be correct here. Okay. Next question. For incompressible flow, continuity reduced to, for incompressible flow, the continuity equation will reduce to whether A, B, C, D, which option will be correct. Just think on that. And I'm looking about the above problem. Okay, just think on that. Actually, whatever here is equation is writing in equation question 8, it is in terms of the vector calculus. Remember, please. So you have to search how to write from the equation, your equation, that is Cartesian equation, in terms of your vector calculus. So you will get the more interpretation or more clarification on that, how these equation write in concise form, because this is very important. Okay, so now I got it, the concept. So before moving on the question number 8, let us discuss on question number 7, how we'll get. So here I have already discussed these two things. What? Your del operator into velocity. So finally you will get del u by del x, del v by del y plus del w by del z. But because in the vector calculus we are writing all three equations, that is in x direction acceleration, in y direction acceleration, in z direction acceleration, in only the single this term. All three equations you have in the single term. What? Let me just explain you here, very easy. I am going to write only the here the convective acceleration, not local acceleration. So u del u by del x plus v del u by del y plus w del u by del z. Similarly, ay is nothing but your u del v by del x plus v del v by del y plus w del v by del z. Similarly, for your z direction, u del w by del x plus v del w by del y plus w del v by del z, del w by del z. Means your acceleration, you have these three terms: axi, ay plus aw. So these three you have in hand. So you are going to write all these three term in a single term. How you will write? Just think on that. So somehow we have come up with this. If you will multiply with del into v, you will get these things. But here UVW, you can write these things also like that: U del by del x, V del by del y, W del by del z. You can write very easily. But here you need, for x direction you need U, for y direction you need W, y direction you need V, and for x direction you need here U, for y direction you need V, for w direction you need, for z direction you need W. So think on that. So how you will come up with this? When you will multiply this term with another u, when you will multiply this term, another u means another v vector, that is a ui plus vj plus wk. When you will multiply, you will get what? Let us multiply this equation with this equation. That is, so u, I will write here u, and when you will multiply del by del x with I, that is ui, you will get del u by del x. Similarly, you will get what? Here is I. Similarly, v del u by del y, j plus w del u by, or you can multiply with one and one term, u del u by del x, and then again u you can multiply like that. That will be very easy. This first term with these all three term with the first, then all three term with second, all three term with third. So let us write del u del by del x, you are getting here u, I plus, then this term I am going to multiply with this u del by del x, v j plus, then this term I am going to multiply with this w del u by del z k. So similarly this term, when you will multiply these all three, similarly when this term, when you will multiply with all these three, so you will get combination of, you just keep I separate, whatever you have I, just keep separate j, that is the j, and just keep separate k term. So you will come up with this equation. You will come up with this ax, that is u del u by del x. Here you can see u del u by del x, or let me just write. Okay, we have written this. Now we'll move on the second one, that is this one. We have multiplied with this. Now we'll multiply with vj. So u, just for your clarification, so here is u del v by del x. Okay, we have multiplied this one. Now we'll multiply this second term with all three. Okay, so you have to very careful. So v del by del y, and you are multiplying with ui, so ui plus then v del by del y vj plus v del by del y wk. Then again with this term you need to multiply all three. W del by del z ui plus w del by del z vj plus del w del by del z, here is wk. So you have to keep this I only, that is take the common. This is I, and this is also you have I, and here also you have I. So you have u del u by del x plus, when you are taking, and v, this is v del u by del y plus w del u by del z. I will be remain. Similarly, plus you keep j, and similarly you keep k. So when you will write k, I am going to write only for k. So the from here you will get, this is k, this is k, and this is also k. So in k also you have u, v, here also you have, okay, so I think here we have some mistake. U, okay, here you have u, because when you will multiply this term with this, u del by del x, u del by del x, and w here. So you will get again u del w by del z, then here v del w by del y, then again here w del w by del z, and here not z, you are multiplying with del x, so here will be the x. So again, when you will multiply with very precisely, so you will come up with your, this will give you this term ax, this will give you ay, and this will give you az. So just think on that. This is the big equation, big three equation you are going to write with the only this small equation u dot del u. Just think on that, how the vector calculus change the notation, the notation of mathematics. Just think on that. So this is very powerful tool. Vector calculus is a powerful tool of, in terms of, you can say, notation, calculation, analysis, everything. So how you will get, I want to give you the clarification on that. So now let us move with the question number 8. So here again, for incompressible flow, the continuity reduced to the continuity equation, just think the continuity equation reduced to. So okay, the continuity equation, as we have discussed earlier also, for incompressible flow, your continuity equation will be this, because incompressible, your rho will be the constant. If rho will be constant, you will come up with del into u. Okay, option B will be correct. Now the next question, in non-dimensionalizing the Navier-Stokes equation, the pressure scale is often chosen as rho u square dynamic pressure, mu, here u is the average velocity, remember, mu u by L viscous scale, rho gl hydrostatic scale, that is your hydrostatic, any of the above depending of the dominated balance. So here in non-dimensionalizing the Navier-Stokes equation, the pressure scale is often chosen. So this is just, I want to give you the option D. Maybe any of the above, which, and depending on the dominated balance. So now let us move with the next question number 1. So here I'll take the 5-minute break, please. So just think on that. I'll take 5-minute break. Okay, so let us move with the next question. So Navier-Stokes equation represent the conservation of which physical principle? So this question is very important. As I have discussed earlier, your second law of Newton's second law of motion, rate of change of momentum, rate of change of momentum. So yes, definitely it is your based on your conservation of momentum. So Navier-Stokes equation are derived from the Newton's second law applied to fluid motion, and they express the momentum conservation in differential form with additional term of the viscous stresses and pressure force. Okay, next question. Which assumption is made for deriving Navier-Stokes equation for Newtonian fluid? Which assumption is made for deriving Navier-Stokes equation for a Newtonian fluid? Stress is proportional to velocity. Stress is proportional to rate of strain. Stress is proportional to density. Stress is proportional to pressure. So these are four options. So just think on that. Which assumption is made for deriving Navier-Stokes equation for a Newtonian fluid? Stress is proportional to velocity. Okay. Because the similar question, but very straight, we have solved earlier, but here little bit twist in the question. So your final answer nothing but will be the stress is proportional to the rate of strain. Option B will be correct here. Okay, anyway, I'll upload the PDF so you can go one by one. So in Newtonian fluid, the viscous shear stress is linearly proportional to this is the equation for Newtonian fluid, the shear stress equation. But here, what is U? What is your V? The Y? So just think on that. As you know, if the water is flowing like that, so your if this is free surface, then your this is your this direction, let us suppose X direction, and this is your Y direction. Not this is X direction, you are measuring at a particular point, this is your U. So how at a particular depth, particular section you think on that, not particular point, at a particular section means what is the velocity here, what is the velocity here, how velocity is changing at each point vertically. So this is your vertical distance. So in laminar flow generally you will get like that. So y here is your depth of the flow. Okay, so viscous in Newtonian fluid, the viscous shear stress, this is your viscous shear stress, is linearly proportional to, this is linearly proportional to rate of strain, that is velocity gradient. And this assumption allow writing the stress tensor in term of the viscosity and the velocity gradient. So very important. Next question. Uh, in incompressible flow, the Navier-Stokes equation include which form of the continuity equation? Incompressible. Here the condition is given incompressible flow. So the Navier-Stokes equation include which of include which form of the continuity equation? Whether option A, B, C or D. Just think. Anyone join? So still no one join. Okay. Anyway, I'll record the video and upload in YouTube. Then you can go with the recorded video, as well as I'll upload the content also in the Google Drive, so you can also go through that. Okay. So as we have already discussed here, your incompressible flow, in incompressible flow, the rho is constant. So your continuity equation, that is this form, del u by del x plus del v by del y plus del w by del z is equal to 0. You can write this equation like this, equal to 0. You can write like that. So option A will be correct here. Okay. Next question. This term rho v, as we have discussed very precisely in the previous question and with the derivation also, just think on that. The term rho velocity dot del operator into again your velocity vector. So this is your vector, remember please. Means this have ui, sorry, ui vj plus wk. So in Navier-Stokes equation, what is represent? As you know, the Navier-Stokes equation is del u by del t. This is, you just think on that, the vector I am writing, vector u plus vector equal to minus del operator p rho g plus mu. Here is right here plus del square u So, but the question is asking about only this term. What will be the term? So, as I have discussed above in the very beginning, the equation, let me just show you. This is this equation, and here also I think, yes, here also we have discussed. And here in the explanatory way you can just see. So what will be the term? We are at question number, yes, here. Okay. So this term, if you will look very precisely, you will think on that. That is this one, your velocity vector, and this, and yes, it is coming on the convective acceleration, and this is your local acceleration as I have discussed earlier. So yes, it is convective acceleration. Which term in Navier-Stokes equation represent the viscous diffusion of the momentum? Viscous diffusion of the momentum. So similarly again, just think on that. Del rho by del t plus v vector. So when you will write again and again the similar equation, you will get some confidence. P vector plus rho, your body force plus viscous force, mu, then del square. So now you can think. So this is your acceleration part, maybe combination of both local and acceleration convective. This is your pressure force, body force, and this is related to your viscous. So question is asking about the viscous diffusion of the momentum. So definitely you will go with this option, this term. So just think, just search this thing, and this is your third term. So here you will get the third term, option B. So option B will be correct. So now moving on the next one, in Navier-Stokes equation reduced to Euler equation. Very important question. Question number 6. Very important. If you have the Navier-Stokes equation and you want to reduce in Euler equation, means your acceleration, rho acceleration is equal to your force. Force is pressure force, body force plus viscous force. So these three force you have in Navier-Stokes equation. But you want to reduce this equation in the Euler equation. So how you will reduce? Means which force you will eliminate? Whether pressure, body and viscous force. That is, your viscosity will be 0, density will be 0, pressure will be 0 and body force will be 0. Very important. Just think. Such type of question you can expect in your final exam also. Very, very important. Okay, so let us move on the final. Here, the viscosity term you will consider zero when you will convert Navier-Stokes equation in Euler equation. When viscosity term 0, the viscous term rho del square V vanish, reducing Navier-Stokes equation in the Euler equation. That is inviscid flow. So here you can say very clearly the assumption for deriving the Euler equation, one assumption should be inviscid flow, because you are not considering the flow have viscosity. But in actually the flow have the viscosity. So that's why we tell the Navier-Stokes equation shows the actual representation of the flow, but not as the Euler equation. Pressure force plus body force. This represent your Euler equation. Very important. Okay. Now, the stress tensor in Navier-Stokes equation is decomposed into a stress tensor. The stress tensor in Navier-Stokes equation is decomposed into pressure stress plus body force, viscous stress plus body force, viscous stress plus pressure stress, and elastic stress into pressure stress, convective stress plus pressure stress, not into plus here also. Just think on that. Okay. So let us move on the answer. So your B option will be correct. The stress tensor in Navier-Stokes equation is decomposed into viscous stress and the pressures. Viscous and pressure stress. Remember. Next question. Which mathematical property makes Navier-Stokes equation difficult to solve analytically? Very important question. Which mathematical property makes Navier-Stokes equation difficult to solve analytically? Analytically means by solving the mathematical equations. Linear nature, non-linear convective term, constant viscosity, steady state assumption. Very important, just think on that. Whether you have to solve linear equation, whether you have the difficulty in linear equation, whether you have difficulty with non-linear equations, non-linear terms, think on that. very important. Okay, so let me just, yes. So I think non-linear equation is very difficult to solve. So definitely, so the non-linear convective term means your velocity, del operator, and this is your non-linear. And what is non-linear in the differential equation? Just please, if you not know, go through some material or videos how non-linearity of a differential equation defined. Then you will think on that, go through these equations. After seeing the concept of non-linearity, you just go through this equation. Let us suppose I am going to write Navier-Stokes equation in x direction. So del u by for incompressible flow, del u by del t plus u del u by del x plus v del u by del y plus w del u by del z equal to minus del p by del x plus rho gx plus mu del square u by del x square plus del square v by del y square plus del square w by del z square. So these are the, just think on that. And this is your convective non-linear term. This is non-linear convective term, and this is make very difficult this equation to solve analytically. This your Navier-Stokes equation is unsolved equation till now, completely analytically unsolved equation till now. Okay, so just think on that, how non-linear make difficult to solve. You just go through some like content or videos also, so you will get more clarity on that. So here we'll discuss about only whether which term make the difficult. Okay, next question. The body force term rho g in Navier-Stokes equation is due to pressure distribution, gravity or external fields, surface shear or convective motion. The body force term rho g, the body force term in Navier-Stokes equation is due to pressure distribution, gravity or external field, surface shear or convective. These are the very basic questions. But yes, at undergraduate level, so generally people not talk about the Navier-Stokes equation. Generally, the Bernoulli's equation, the limitation, most of the cases, the limitation up to the Bernoulli's equation. But so that's why I'm discussing here very simple question here. So just think on that, which option will be correct. Body force term rho g. Yes, this is due to your gravity and external field, remember. Option B will be correct here. Next question. Which of the following is a simplified form of the Navier-Stokes equation used in lubrication theory? Here is the new theory that is we have not generally discussed, the lubrication theory. which of the following simplified form of Navier-Stokes equation, which is used in the lubrication theory, Euler equation, Reynolds equation, Bernoulli equation, or energy equation? We have four equations, so just think on that. Okay, so I'll not get delay in this question. Yes, Reynolds equation. For a thin film lubrication, Navier-Stokes equation is simplified using lubrication approximation, means leading to Reynolds equation. So remember. Next, so here I have very simple numericals. A viscous incompressible fluid flow between two infinite parallel plate. Distance h parallel infinite. Parallel infinite means this type of parallel we are talking about. Infinite means the again there is a lot of length. Then parallel, where the question is talking about parallel. So these are your parallel plate. So these are your parallel plate, and the distance between this parallel plate is here to here is 5 mm. And viscous incompressible fluid in between, in these two plate, your viscous fluid is flowing. Okay, with the pressure gradient, if this is your x direction, means your pressure changing in x direction, total change 200 means decreasing Pascal per meter, and viscosity is given 0.001 Pascal second. Means your pressure gradient, that is pressure dropping when you are moving from in x direction. This is your x direction. So find maximum velocity. Maximum velocity you need to calculate. How you will calculate, just think on that. Viscous incompressible fluid. So just little bit 1 minute you can think. Viscous incompressible fluid means you have to think on that. Your rho is constant. So which equation you will apply here? Okay, so I will just show you the answer. So anyone join? I think. Okay, no one. Okay, so here for the flow between two parallel plate, you have equation like that, your velocity equation. dp by dx h square by 4 minus y square. So this is your final equation. I think sir have already told and also teach you very clearly. So you when you will calculate u max, so u max you will get at your y is equal to 0. Y is equal to 0 means what? This is your h. So you are measuring y from here to here. This is your 0 line. This is your y. So based on this assumption, this formula is derived. Remember please. You can also assume, if you want to derive your with your concepts, so you can also assume y varying from here to here. So based on that you will derive the formula. So this formula is derived like that. So at y is equal to 0 you will be the maximum, because at the plate your velocity will be 0 because of the no slip condition. As you will move from away from the plate, your velocity will be increase. So that's why here you will get the maximum velocity. So after putting the all values, whatever you know, that is, you know the your viscosity 2 mu, and you know already the pressure gradient, and you know already your h value, and after final calculation you will get 1.25. Maybe the calculate, you just check the whether calculation is correct or not, but concept will be the same. So option B will be correct here, remember. Next question. Water with your density 1000 kg per meter cube, dynamic viscosity 0.001 pascal second, flow steadily in pipe of radius 0.05 meter with mean velocity 0.2 meter per second. Find the pressure drop per meter length. Here you need to calculate the pressure drop per meter length. Means del P by dP by dx you need to calculate. And you have the pipe with radius 0.05, mean velocity, you have the average velocity. So here you need to the formula with average velocity relation between the del P by del X. So find the pressure drop per meter length. Which option will be correct? Means you have one pipe, with radius 0.05 meter, and the velocity in the pipe is 2 meter per second, and rho is given 1000 kg per meter cube, and mu is given 0.001 pascal second. So pressure drop you need to calculate. So for that you have some relation between del P by del X. Okay, so will not take much time. So let us, I will show you the relation. Here is your relation. This is del P by del L, del P by L, that is change in pressure with respect to that is per meter length, is equal to 32 mu. This is your average velocity divided by d square. Here you can, one thing you can also write, per meter length means L is equal to 1 is given, 1 meter. So once you will put this formula, once you will put the data in this formula, so your delta p is nothing but delta p you have to calculate, and 32 mu is given already 0.001, velocity is 0.2, and your d square means diameter, and you have radius 0.05. So radius is nothing but d by 2, so diameter is 2r, so you will get 0.01, 0.1, not 0.1. So that's why here 0.1 square d square. So after calculation you will get 64 Pascal per meter. Remember. Okay. Now let us move with the next question, number 13. Very important. A soot flow occur between two plates separated by 0.01 meter. The top plate move at 1 meter per second. Top plate is moving and the bottom is stationary. Find the velocity at mid plane. Means you have one plate with moving velocity is 1 meter per second. Another plate you have means top plate, and the bottom plate you have a stationary. This bottom plate is stationary, means velocity of this plate is 0, and the distance between the plate is separated by 1 meter, no 1 meter, 0.01 meter. So bottom is stationary. Find the velocity at mid plane, means here you need to find out at mid. So as you know, if the distance between the plate is very small, we can assume the linear velocity distribution like that. Linear distribution. If this is your height is h, let us assume the height is h, so you have to calculate your velocity at h by 2. So at h, this is your 0, h is equal to 0, and this is your h is equal to 0.01, and at h is equal to 0.01 your velocity is 1 meter. So you have this equation, this question you can think this is analytical type question, so you can think on the gate type of questions or your final exam of NPTEL also. So here you have 1 meter, 1 meter per second, and h value you have 0.01. So at middle here 0.005 you have to calculate your velocity, and here h equal to 0, your velocity is also 0. So you know already the triangle law, very important. So this and this will be the same, means the ratio of these two, 1 by v, is equal to ratio of this distance 0.01 divided by this 0.005. This is the triangle law. So you can write from here, this will give you the 30, and you will remove this will give you the 20, 20, 20, so 5 to that 2 times. So velocity is equal to 1 by 2 means 0.5. So hopefully option B will be correct. Yes, option B will be correct. But how? Just I have shown you. Or you can approximate like that also. But this is from just your general understanding how you will solve. And here also you can think. Now let us move on the, and how this is valid, you can validate also. U is equal to, that is, U is a function of Y is equal to capital U, means your top velocity divided by H, that is the height of your pipe, that is the height between the plate, and Y, that is Y start from 0 to H. Y will be from 0 to H. So once you will put Y is equal to H, then what will happen? Your U H is equal to U, because here will be the H and again at the place of Y will be the H, so things will be the same. U by U equal to U. So here also you can think. Now let us move on the next question. A fluid dynamic viscosity 0.002 Pascal second is confined between two parallel plates 5 mm apart. The lower plate is stationary and the upper plate move at 0.2 meter per second. Find the shear stress. Similar case here. You have two plate. The lower is stationary. So I will draw very, and above one is moving with the velocity is 0.2 meter per second, and dynamic viscosity you have 0.002 Pascal second, and 5 mm. The distance between the plate is 0 in meter, 0.005 meter, or you can say 5 mm. Okay. Find the shear stress. So tau is equal to, you know, dynamic viscosity and del U by del Y, means if the situation like that, you can assume velocity by Y, tau. Find shear stresses, but shear stress at where, whether in middle, where in the top or bottom. Okay, let us see. Tau is equal to nothing but your mu, whatever I have written here, just in the simplified way, mu velocity by Y. A similar thing, mu velocity by H or Y, you can say. So dynamic viscosity is, so you are calculating at top. Remember please, here in the question is asking find shear stress at H is equal to 5 mm. So here if you will put tau is equal to 5 mm, 0.002 into velocity is given 0.2, and here is a 5 mm, 5 meter. So again you will get here 30, and here also you will get 30. So this will be the cancel out, and 2 to the 4. Again you will get 10 here. 2 to the 4, 4 by 50. So when you will divide, you will get 0.08 Pascal. Very important. So these are the concepts. So okay, this is the last question for today class. I study laminar flow in a pipe of radius r. The velocity profile is this. Velocity profile you have ur is equal to u max. U max will be at the middle, capital R by R square. Find the average velocity. U average you need to calculate. Very important. How you will calculate U average? Because your velocity profile is like that, parabolic. When you will average this parabolic, this graph will convert like that. You have to convert this graph like that. How you will average? The averaging means this. Everywhere the magnitude will be the same. Here is magnitude is less, 0. But here you have some magnitude. Averaging means this. At the place of 0, you are going to put some values, which is equal to the maximum values also. This is your maximum value. But here is everywhere is the same value. The averaging means this. How you will average this equation? So just think on that. So okay. So average means nothing but your, here you can say the averaging concept. One thing here is you need to remember your U average in case of pipe flow, very important. U max divided by 2, or you can say U max is 2 times of U average. This is also important. And how you will average these things? So let me just, I'll give you some conceptual illustration. You can think on that. If this is R, if this is capital D, and from here your radius is R, this is radius R. So how you will calculate the thing? You will just take a small piece and you will differentiate on that, and once you will add these things, you will get the final your final answer. So similar concept here, here we have used for averaging. For averaging, the integration means what? Integration means summation. So you are summing this particular, this is also the very differential element you are summing, means, and after that you are dividing with, you are dividing because you have the similar profile here like that and here like that. So we are discussing only half part. So you are dividing with R. So you are adding these all things, you are adding and dividing with R. So similar, these are the concept. If you are not getting, so similar concept I'm going to, I'll discuss in the final, the extra session whatever I will take. I think extra session I'll take on the 15, on 15 October. So on that day I'll discuss very clearly. So thank you for today. We'll meet again in the next class on tomorrow. Next class is your tomorrow. So thank you.